some remarks on configurational mechanics, but then I'm expert.
Another one.
Yeah. The outline is in this way that we have some historical remarks.
Thank you.
And then the contribution of remarks to configurational mechanics. I will not this part of the content short because I know therefore I need the rest of the time to give some ideas of what I did together with co-workers in the field of reciprocity in material space. Okay, now I'm equipped. I doubt if this works at all, but maybe you can hear me better. Okay, historical remarks. I do it in this way in pre-Eshelbyan history, Eshelby, and post-Eshelbyan history. Some this is rearranged slightly by there's not really compatibility between my stick and the computer here, but I think it doesn't disturb too much. What you probably all know is that thermodynamic potentials, driving forces, thermodynamical forces were at least been introduced by Gibbs and Helmholtz. But Lev-Trostianowski drew my attention to works of Weierstrass and Erdmann. They studied jump conditions and they introduced already those driving forces. Later on in 1950, Peach and Köhler, it had been already there, the force on a dislocation, and this is a very famous paper. And then Eshelby came. Eshelby, with his pioneering work on the force on an elastic singularity in the philosophical transaction of the Royal Society in London, and Eshelby introduced this concept, but there was no real big effect until the J integral of James Rice came up, and then he claimed that everything he had already done, and he was very upset that his contributions were not paying so much credit. The community didn't pay so much credit. This changed completely after he passed away. Now we have Newtonian mechanics and Eshelbyan mechanics, and he introduced his energy momentum tensor, or he called it Maxwell tensor of elasticity, and he did not call it Eshelby tensor, but we do it now. This is the Eshelby stress tensor. This is in his original writing, the introduction of this tensor. And this tensor, when evaluated around a closed loop, around a singularity, gives the force on this singularity. And this can be interpreted in the following way. If you have in a body some singularity, for example a cracked tip, or a dislocation, and this dislocation is displaced a little bit by changing the configuration, then the energy will change. And if you differentiate the energy with respect to the position of the defect, you get something out what has the dimension of a force. And it is this material force that is called driving force in this way. If the defect can move within the material, it will move, because it can reduce energy. It's like if you're putting too much pressure on your students. They just try to escape somehow. Every material is like a smart material. They want to release energy and get off this pressure. And this integral over this Eshelby tensor tells you the driving force on this. Okay, then we have post-Eshelbyan history. Irwin immediately took up this concept and calculated the force on the crack tip by using the Eshelby tensor and the near crack tip field. He didn't introduce a J integral, but he expressed these forces on the defect by the stress intensity factors that those people are working in fracture mechanics are very well aware. Okay, in 1962, Günther introduced also path-independent integrals. I talked to him and he said he had no idea what this might good for, and therefore he hid his contribution somehow in the wissenschaftlichen Abhandlungen der Braunschweigerischen Gesellschaft. And therefore it was not discovered, or nobody took care about this. Then the start of the application of these material forces and path-independent integrals became really working with Rice. I think it was 1968 when he introduced the J integral, and there was a lot of controversial discussion with Cherepanov, who also introduced similar things. But anyway, as history walks along one path, it stays at this path and is still contributed to Rice, this J integral. And there are a lot of other things happened. For example, Knowles and Sternberg extended this to linearized and finite elastostatics. Budiansky and Rice discovered J, L, and N integral, which are completely identical to Günther's integral, but there had been known that this was extended to elastodynamics and so on. And then, as Dietmar Groß put it, the golden age of material forces started in the 80s. Thermodynamic forces, configurational forces, material forces, Eshelbyan forces, everything is the same. And the subject was so much matured in these years that already textbooks appeared on material forces or on configurational mechanics. Gerard was the first, with 1993 on his book in Material Inhomogeneities in Elasticity. He had a very precise continuum mechanical view on the subject. Morten Gerten had a book in 2000 who had a different view on the subject, which we will not discuss now. And George Herman and myself, we had also this book in 2000, and we took a more engineering directed view on this subject and gave some applications. Okay, and many others contributed to this concept of material forces and material mechanics or Eshelbyan mechanics, and I don't want to mention anyone because I have the feeling if I forget someone from the audience, maybe they don't speak with me anymore, even beat me afterwards, or therefore no further reference to that. And then in 2011, Gerard's masterpiece appeared after almost 20 years after his first book. He rewrote the concept completely, and he gave a lot of contributions. For example, he just juxtaposed the Newtonian mechanics and Eshelby mechanics in a very precise way. He had applications, elasticity and thermodynamics. Since Gerard is very much educated as a physicist and not like me as a poor engineer, he has the whole field theory at hand, and he can do things in electromagnetic ferroelectric. One of his specialities are waves and solitons, and as you see today, we had already this generalized continua, polar, microstructural, micromorphic. Biomechanics is not included. I think in the book there's no biomechanics. It is, okay, it is hidden behind these last 3 points and so on. And what I would like to mention, especially that he also gave contributions to numerical applications. Yeah, he gave hints how to improve the nets, the finite element nets and measures by use of this general concept of Eshelby mechanics. Okay, it's enough or some more? It's enough. Okay, good. Then I'm going to talk about reciprocity in material space. This is joint work with the late George Sherman. The beginning of this work we did together, and later on my co-worker Roland Schröder helped me when we went to numerical applications. George and I did our problems with paper and pencil. Okay, as you all know, reciprocity, Bessie, Maxwell theorems is the following. If you apply a force, we are now in physical force, in physical space, we apply a force F1 at position 1. This causes also displacement of a point at a different position. There are two indices for the displacement, U1 here and here. The first index is where, and the second is where from, why. Okay, this is the displacement of the point 2 due to the fact that at point 1 a force is applied. And this is the displacement at point 1 due to a force applied at point 2. And you all know that the work of the force F1 exerted in the displacement at position 1, but due to the force 2 is equal to the work of the force 2 times the displacement at position 2, but due to the application of the force 1. Since the displacement at position 1 due to the force F2 is proportional to F2, and this one is to F1, you can introduce this influence coefficient. The same happens in material space, but there's one small difference: cause and action. The cause of here is the forces F1 and F2. And the result of the forces is the displacement. This is changed in material place. The cause is the material displacement of a defect at position 1 and 2. And the effect is that the material forces at this position change. Therefore, the material force B21 is the change of the material force at position 2 due to a material translation of defect 1 and vice versa. And therefore it does not work very good. This equation reads correctly that the lambda 1 acting in B12 is equal to the lambda 2 acting at B21. Hopefully it will work in the next slide better. There is some incompatibility. Okay, being more specific, we study an interaction problem between two defects, a hole and a dislocation. The dislocation strength is given by the Burgers vector B, and the hole is given by the radius R0. There are two defects, and they can act on each other. And you can calculate the J integral in the following way. You apply a material translation of the hole. How does this happen? That's not my problem. This might be dissipation or something, whatever you like to. Yeah? But this hole can move by an amount of lambda 1. And if you divide the change of the energy, you have two configurations. One is the hole is at position x1, and then it's shifted. That's a different configuration. You have different energies, and if you subtract both energies and divide this by lambda 1, you have just the J integral. You can calculate the force on this defect by a path-independent integral, including this defect, and you can find immediately the force on the defect with the hole in this direction, what drives the hole into this direction. Okay, going back to the initial configuration and applying translation in x2 direction by lambda 2, you have the integral J2, because J is a vector valued energy release rate depending on the direction. If you have a rotation of the defect with respect to some reference point, you can calculate the change of the energy due to this rotation by the L integral, and the M integral is the change of the change of the integral by blowing up in a self-similar way this hole, and this is M integral. And then you can establish several reciprocity relations. I will give only 2 examples. There are 6 at all. The first reads as following: the change of the J integral in x2 direction, the force in this direction, changed by a translation of the defect in the one direction times the material displacement lambda 2 is equal to change of the J integral in this direction due to a change of the configuration, the force in x2 direction times this material. And again, since if you have small material translations, the change due in J2 due to a change of lambda 1 is proportional to lambda 1, and therefore you can immediately introduce influence coefficients. Another one is what we will need in the following is if we have look at the self-similar expansion of the hole that is given by this parameter alpha, then we can give the following reciprocity relation that I will use in the following. The change of the J integral in this direction due to a self-similar expansion of the hole times this lambda 1 is equal to the change of the M integral due to a translation of the hole in lambda 1 direction times this self-similarity coefficient alpha. Okay, and as Girard put it some time ago, the beauty of the theory is inversionally proportional to its usability. But this theory is not as beauty. There are some applications still possible. For example, let us look for a crack and holes. And we would like to calculate influence surfaces. That's the following. We would like to know how does the crack driving force changes if this hole is increased by self-similar expansion. You may maybe this might be a melting process, or you can a mouse have sitting here in Swiss cheese or whatever you like to. This hole can increase its radius. Therefore, we would like to calculate. There are 2 things. You can calculate if you apply a stress. You can calculate the J integral, and you can calculate the M integral. And the question is, how does the J integral changes due to an increase of the hole in this position? And you can calculate this delta J. Okay. On the other side, you can also calculate the change of the M integral due to a change of the crack length. And due to reciprocity, you have this relation, yet you have the change of the radius of the hole times the change of the J integral is equal to alpha times the change of the M integral. And this has an immediate consequence, because if you are not only, if you would like to calculate this here, you have to remesh, have the same mesh but a bigger hole, and you calculate the delta J. But if you would like also to calculate the change of the J integral due to the increase of this hole and that hole and that and that, you have at any time you have to remesh and calculate the energy and do the difference. Due to reciprocity, you just calculate the change of the M integral at any point here due to a change of the crack length. And due to reciprocity, you can calculate by one remesh all these difference in the D. This D should be a delta. I don't know why, how this happened. Okay, this is one of the advantages of reciprocity. And we made a build-up post-processor for this problem. And here we just checked if the influence coefficients are the same, if you increase the hole or you extend the crack. And we just checked that it's working, and then we did some examples. For example, using reciprocity, we had calculated an influence surface. Therefore, if the hole is at any point here is increased, you can immediately see from the value at these grid points how the crack is changing. And therefore, you see that not the crack in front, the hole in front of the crack is most dangerous, but cracks that are inclined by something like 45 degrees. And you can see also crack shielding. If you have here a crack, a hole in top of the crack tip, and you increase the hole, the J integral will diminish, because you have this shielding effect. This white part here is where we have no numerical values. This will be improved more, but we didn't want to discuss asymptotic behaviors. Okay, next example, we have an array of holes, and you see the most severe hole is this one. Not this one, but a hole in this direction where you can immediately see by this influence surfaces which of the holes are the most dangerous one. You can also have interaction between cracks. That is not really academic. You can see those crack configurations in ceramics. I saw this picture, but I forgot the PhD students to ask for permission to produce a paper here and show it to you. I will do this, and if it's happened that you hear this talk another time, you will have this real application from this ceramics part. Okay, we have to understand what comes out. You have all these small cracks here, 10 up and 10 down. And we first calculated, that you get an idea what happened, is we calculated the individual J1 integrals if we apply stress in this direction. And this is the red curve. What you see is the position of the crack going from here or here, working to the symmetry plane here, to there, and you see that the J integral of the individual small cracks due to the presence of the large crack is distributed in this way like the red curve. And you see that not this curve gets the most, but about one crack in this 45 degrees. And if you now increase one of these crack tips, one of these cracks in direction of the other crack, then you see that the influence on the main crack is not the influence of the center crack is almost zero, yeah, but the influence of the center crack is in somewhere here or here, and therefore you can just discuss and find out interesting results. And we did this also for rosette of cracks. In a similar way, there are a lot of cracks, and you see here also shielding effects. The cracks in this direction are shielding this main crack, and you find even this one, if you extend this one, it is shielded so much by the others that the J integral reduces. If you extend this crack here, you have a large effect on this configuration. Okay, this was also only just to give you some idea what you can do in material space. Only one small example there, as you see, for example, biomechanics, and so you can work a lot in this field, and I invite you to join these contributors in material mechanics or Eshelby mechanics. Thank you for your kind attention.
Questions?
Something also always puzzles me. You use linear elasticity at the crack tip. Apparently it somehow works, but I would expect very large stresses at the crack tip, and to say that this should be modeled non-linear elasticity. But how is it working? Why?
You know, linear fracture mechanics is well established, and since you have, for example, if you use the integral around the crack tip, only the singularity is included, but not the exact value of this. It only needs to come through by the net that there is a singularity at this point of the crack tip. And if you model the crack tip correctly, then you can calculate it by fields far away, and it works. For example, the stress intensity factor is not the value of the stresses at the crack tip. It is only the value how the stresses go with 1 over square root r to infinity. It's a prefactor of the singularity. And it turns out that the material knows something about stress intensity factors and behaves like it. Yeah, of course there are singular fields involved, but everybody knows that if you only look at a cracked specimen and you have, by this looking, infinite stresses, this can't be a good failure criterion. But the stress intensity factor, and related to that the J integral, they are good failure criteria for brittle fracture mechanics.
Are you saying that you replaced linear theory with some nonlinear theory near the crack tip?
No, I don't.
And it's linear outside that it works? So
No.
That's what you mean when you say it works?
No. With these solutions, the stresses are infinitely large, but we don't care. And we say, okay, we know that infinite stresses are impossible in real materials. But there happens something in a process zone or whatever you like, and outside this process zone you have linear elasticity, that the singularity is embedded in a linear elastic field, and the failure criteria work.
Well, of course, they solve a linear elasticity problem, and it's incompatible with linear elasticity.
Who cares? We don't care.
You treat some kind of small increment, small variation.
Yeah.
You sort of not observe the change of direction of the tip of the crack.
No, this is not here included, but you can predict the direction of the crack if you have a hypothesis based on the J integral vector, that the J integral vector points in this direction where the most energy is released. Yeah. And then you have to go pointwise. Maybe there is a last question.
Does this mean that, for example, if you want to use finite elements here, that in order to compute the driving force for the crack evolution, it's not necessary to have a fine mesh at the crack tip, but it's sufficient to have to compute the stresses correctly at a sufficiently large distance from the crack tip?
Normally we use coarse meshes, but we use special crack tip elements. We put a rosette of finite elements around the crack tip, and they are 8-noded elements. They are collapsed. One of the sides is collapsed to 1 point. Therefore, 3 points are in one, and the midpoints are shifted to the quarter point position, and these elements build up the 1 over square root r singularity exactly. Therefore, we can have these results with quite coarse meshes.
What can you say about if the holes are very close to the crack tip? If the holes are very close to the crack tip, can you say anything more about that?
We can, but not in this approach. Okay, we did several things in this direction, and but this is not included in this talk. For example, myself and also Xantippe Markenskov, she studied asymptotic behaviors of if these two holes come very far near together, or a crack and a hole, and what happens there asymptotically.